The first lesson in Chapter 8 introduces us to three different types of variation models. We'll look at direct variation first, then we'll look at a joint variation, and then we'll actually end with an inverse variation. It's the inverse variation model that is kind of the motivation for the first half of this chapter and why we didn't teach this lesson at any point sooner in the chapter, is that it kind of fits with what we're going to go into again in the first half of this chapter. The first of these variation models is called a direct variation. It is one that can be written of the form y equals k times x, where k is called the constant of variation. Or sometimes it's called maybe the proportionality constant, but they're easy to recognize this type, and actually it's easy to recognize any of the types of models we'll go over today, because you'll read in the problem that something, it'll generally say, varies directly. Something varies directly with something else. But you will see within the text of the problem the words varies directly, which is going to lead you to that mathematical model. For the first example, let's just take one that specifically uses variables y and x. It says, suppose y varies as x, or maybe you should say y varies directly as x. Probably a word that needs to go into this slide. So if y varies directly as x, that's the model y equals constant times x. So we're asked to find the value of y if x equals 12. Let's actually write down everything that we know. We're asked to find the value of y when x equals 12 if when y equals 4 x equals 36. So there is our known and unknown values. Now there's two ways to do this problem, and I'll show you both techniques here on this first slide, and then you can decide which of those two techniques that you like, and you can practice it as you do your homework problems. So here's method 1. Method 1 will involve finding the k. Find the value of k. So the first thing I'm going to do is I'm going to take my completed xy point, 436, and I'm going to plug them into x and y in this equation and find the k. So it'll be 4 equals k times 36. To solve for k, we divide both sides by 36. So we get k equals, if we reduce that fraction, 1/9. Now that's not actually the answer, because it's not the final answer, because we haven't found what y equals. But that makes our model y equals k times x become y equals 1/9 times x. Okay. Well, now we could take this 12 that we have for x, substitute it in for this model, and find the y. So we have y equals 1/9 times 12, which would be 4/3 reduced. Okay, so again, that's the first method, where we actually find the value of k, find the numerical value of that constant. Method 2 is just simply a proportion technique, where we don't find the constant. If you look at this equation here, it can be rewritten as k equals y divided by x. Okay, solving this for the k, I just divide by the x. Okay, so y divided by x, what I'll do is just take, very simply here, I'm going to take the y divided by x of the values I know and set them equal to y divided by x to include the value that I don't know. And now I've got a proportion where I can cross multiply. This is 36y equals 48. I divide both sides by 36. Fraction reduces to 4/3. And you see, either way, I got the same answer. I generally, unless I'm asked to find the constant of variation, I generally prefer to do this method too. It just takes the constant out and we don't have to worry about it. It's kind of more of a direct approach. This next example on direct variation says the cost of an item in euros, E, varies directly. So again, you see within the text of the problem it's going to tell you how it varies. Varies directly as the cost of the item in dollars, D. It's kind of like saying y varies directly as x, just like in the last problem. So we can set up a model that says instead of y equals constant times x, we'll use the variables here and we'll go with instead E varies directly as D. Okay, so what's the known information? The known information, it says that E equals 3.85 when D equals 5. And then it tells us when E equals 10.00, D is unknown. So that's what we know and what we're trying to find. So again, the way I like to do this, this is going to be the method 2 approach from the last slide, is I'm going to resolve this equation for the k. K, if I divide by D, K would be E divided by D. So I set up my proportion with euros divided by dollars, okay, using these numbers over here. So it's going to be euros 3.85 divided by dollars, which is 5, equals euros 10.00 divided by dollars, D. Okay, so we cross multiply 3.85 D equals 50.00. Divide both sides by 3.85 and D equals, I'll go ahead and use the calculator on this part. So let's see, D equals 50 divided by 3.85. I get about 12.99 dollars. And the next variation model is called a joint variation. It's one that's of the form y equals k times x times z. It's kind of like a big direct variation. Okay. K is still just a constant of variation. Oftentimes we'll work without the constant, as we can set up kind of a similar type of proportion like with the last type. And you'll read within the text of the problem, you'll read that something varies jointly with other things. So you're going to read in the text of the problem the word joint variation or something similar to it that's going to lead you to this model right here. Okay, so let's just go straight to an example to see how this has worked. Okay, the example problem says the volume V of a cone varies jointly. So there we see the type of variation within the problem, varies jointly as the area of the base B and the height H. Complete the table below. Okay, so let's write out the model. Instead of using y and x and z, we'll use these letters within the problem, and it'll be the the volume V varies jointly with the area of the base and the height. Or, because I'm going to go with the proportion strategy, the constant equals the volume divided by the B and the H. Divide by both of these, we get K by itself. Okay, so that's my relationship between all the variables within the problem. So, setting up a proportion, and these are the numbers I'm going to use for the V, B, and H that I see right here. It's going to be 12 pi divided by 9 pi times 4 equals, so that's my V divided by B times H. I'm going to do the same thing with these numbers. V, 24 pi divided by B, I don't know, H I do know. Okay, so we'll cross multiply. That's going to be 12 times 9 is 108, so I'll have 108 pi times B equals, and I need to do 24 times 9 times 4 on the other diagonal. I get 864 pi squared. Notice there's a pi times a pi here, pi squared. Divide both sides by 108 pi. That gives me B by itself. 864 divided by 108 is 8. Pi squared divided by pi is pi. And the units looks like the units of the problem is in feet. The last variation model is kind of, again, as I previewed, the one that kind of previews where we're going in the first few lessons of this chapter. It's an inverse variation model. It's one that's of the form y equals constant divided by x. Okay, that's a new type of function. That is something that we call, kind of previewing a few sections ahead here, a rational function. A rational function is one where the x, the independent variable, is in the denominator of the fraction. We haven't seen one like that before. And we'll study its graphs much later in this chapter, but just to kind of show what it looks like, first quadrant anyway, typically a graph like this, a function like this, will look like this in the first quadrant. And usually there's a curve down in another quadrant somewhere as well. But it has the property that as x increases, okay, notice as the x values here are increasing, the y decreases. Notice that as I go out to the right, the graph is coming down. And that's true of an inverse variation model, that as one value goes up, the other value comes down. They've got kind of this, let's go this way. As one goes down, the other is going up type of relationship between the variables. And we'll see just that in the next couple examples. First example reads, suppose y varies inversely as x. So we're going to see the language of choosing which variation within the problem. So if y varies inversely as x, we set it up as a division type problem there. That leads us, I'm going to show where I'm going. I'm going to use the same kind of proportion technique, although it's not really going to look like a proportion this time. If I multiply the x across the equal sign, that leads us to the relationship k equals x times y, and kind of taking the k out of the solving process of this problem. Let's write out what we know and don't know. We know that when y equals 6, x equals 16, trying to find the value of x, when y equals 2. We're going to plug these numbers into this. Okay? And how's that going to look then? We're going to have x times y, 16 times 6, that's the x times y, equal to the other x times y, which is x times 2. We now have an equation we can solve for the x. Divide by 2. So x equals, this is going to be 48. And you can see kind of what has happened as the y value went down in value from 6 to 2, the x value increased. So as one variable decreased, the other variable increased. That's an inverse variation model. Okay, next example that says the time needed to complete a certain race. So let's just kind of identify our variables. The time needed to complete a certain race varies inversely with the runner's average speed. Okay, so time varies inversely as the runner's average speed, or the constant equals s times t. Okay. So what do we know? It says here that if a runner's average speed of 8.82 miles completes the race in 2.97 hours, so plugging into here I'd have 8.82 times 2.97. What's the average speed? What's the S when a runner completes the race in 3.5 hours? Okay, so notice time went up, speed should go down. Let's do this, and I think we'll use the calculator for this. I'm going to divide both sides by 3.5. So S equals, I want 8.28 times 2.97. I'm going to divide it by 3.5. I'm going to say it's 7.03, and this is speed, so miles per hour. Okay, this last example is here just to show you that we're not solely tied to one type of variation model when we work these problems out. Oftentimes models are mixed together. This says the owner of a bookstore developed a model to determine the price of rare comic books. The price P, okay, so the price P of each book varies directly with the number of people that have requested the book, and inversely to the number of such books in existence. Okay, so the price P, it varies directly with the number of people, that's a multiplication, and inversely, that's a division, with the number of books in existence. Okay. Rework this to solve for K. To solve this for K, I'm going to multiply the M across, and we're going to have to divide by the N. Okay, so there's our model, how we can relate the price, the number of people, and the number of books in this problem. Okay, so this first sentence tells me, the first part of the sentence says, if when n is 10, m is 10,000, p is 5. So let's plug those in. P is 5, m is 10,000, n is 10. Find p when m is 100 and n is 200. So let's see, to solve this for p, I'm going to have to multiply both sides by 200 over 100. Cancels the 200, cancels the 100. So it kind of looks like this then. P equals 5 times 10,000 times 200 over 100 times 10. Okay, you can go to the calculator if you want, or you can start reducing this, I suppose, if you want. Let's see, these multiply to be 1,000, and then 1,000 goes into 10,000 10 times. So it looks like we have 2,000 times 5. So I'm going to say that the answer is 10,000. Okay. Yeah, does that make sense with what you'd think if there are only 100 copies of a comic book and 200 people want it? That comic book's probably going to be pretty expensive. On the other hand, if there are 10,000 copies of a comic book and only 10 people want it, well, that comic book's not very popular, and therefore it's not going to cost very much. So yeah, that kind of makes sense if I think about what I've actually just solved for.